Welcome to the world of machine learning. Today, we're breaking down the absolute essentials you need to know. Whether you're just curious or starting your ML journey, this video will guide you through the core concepts, from the main types of machine learning to how data is prepared and models are built. We'll use simple analogies and real-world examples to make everything clear. By the end, you'll understand not just the theory, but also the practical workflow engineers use to create smart systems. Let's dive in and demystify the basics of machine learning together. Machine learning isn't a one-size-fits-all approach. In fact, there are three main types, each with its own unique way of learning. Imagine different teaching styles. Supervised learning is like a teacher getting a student, unsupervised learning is a student exploring on their own, and reinforcement learning is a dog learning tricks with treats. These three pillars form the foundation for all machine learning systems, shaping how algorithms interact with data and learn from it. Understanding these types is the first step to grasping the bigger picture of ML. Supervised learning is the most common type of machine learning. Here, the algorithm learns from a labeled dataset, much like a student learning with a teacher. You provide the computer with questions and the correct answers, and it figures out how to map inputs to outputs. For example, you might feed an AI thousands of emails, each marked as spam or not spam. The AI learns the patterns that distinguish spam, so when a new email arrives, it can accurately label it. This approach is widely used in real-world applications, from email filtering to medical diagnosis. Supervised learning is all about discovery. In this approach, the computer is given unlabeled data and left to find patterns on its own, without any guidance or answer key. Imagine a student exploring a new subject without a teacher. For instance, you might give an AI a huge list of customer purchasing habits. The AI naturally groups customers into clusters like budget shoppers, tech enthusiasts, or holiday splurgers without being told what categories to look for. This method is powerful for uncovering hidden structures in data. Reinforcement learning is all about trial and error, driven by rewards and penalties. Here, the AI, called an agent, interacts with its environment. If it makes a good move, it gets a reward. If it makes a bad move, it gets a penalty. Think of a dog learning tricks with treats. This is how AI learns to play video games or drive autonomous vehicles. The agent tries millions of random moves, keeping the actions that lead to the highest scores. Over time, it learns the best strategies for success. The heart of every machine learning project is the dataset. A dataset is simply a collection of data, organized much like a massive Excel spreadsheet. It can contain numbers, text, images, or even audio. This dataset is what you'll use to train, test, and evaluate your machine learning model. Think of it as the raw material, the fuel, that powers the entire ML process. Without a well-organized dataset, it's impossible to build a reliable model. Working with a dataset, you never show the entire thing to the computer at once. Instead, you split it up. Training data is the largest chunk, usually about 70 to 80% of your dataset. This is the actual material the AI studies to learn patterns and build its brain. By focusing on this portion, the model can practice and improve before being tested on new information. Training data is essential for helping the AI understand the relationships within your data. Testing data is a hidden slice of your dataset, usually making up 10 to 20%. The AI never sees this data during training. Once the model has finished learning, you use the testing data as a final exam to see how well it performs on completely new, unseen information. This step is crucial for evaluating whether your model can generalize its knowledge, rather than just memorizing the training data. Validation data acts like a practice quiz before the final exam. While the model is training, engineers use validation data to tweak the model's settings, called hyperparameters, and check if it's on the right track. This helps ensure the model doesn't just memorize the training data, but actually learns patterns that will work on new data. Validation data is a key tool for fine-tuning and improving model performance. Feature is an individual measurable property or characteristic of the data you're analyzing. In a spreadsheet, features are your columns. For example, if you're building a model to predict house prices, the features might be square footage, number of bedrooms, zip code, and year built. Features are the building blocks that help the model understand and make predictions about the data. Label is the final answer or outcome you want the AI to predict. In our house price example, the label is the actual selling price of the house. Labels are what supervised learning models try to guess based on the features provided. They are essential for teaching the model what the correct output should be, getting it during the training process. The term target variable is just the formal statistical name for the label. When you're training a model, the target variable is the specific value or category the model is aiming to calculate or predict. Whether you're forecasting house prices or classifying emails, the target variable is always the main focus of your predictions. Now that we've covered the basics of data, let's look at the main tasks machine learning models perform. These tasks are grouped into two categories: supervised learning tasks like classification and regression, and unsupervised learning tasks like clustering and dimensionality reduction. Each task serves a unique purpose in the world of ML, helping us solve different types of problems. Classification is a supervised learning task where the model's job is to predict a discrete category or label. It's all about putting things into buckets. For example, binary classification involves choosing between two options, like is this tumor benign or malignant? Multi-class classification expands this to multiple options, such as is this an image of a cat, dog, or bird? Classification is widely used in everything from medical diagnosis to image recognition. Regression is another supervised learning task, but instead of predicting categories, it predicts continuous numeric values. For example, you might use regression to forecast the exact price of a stock tomorrow, estimate the temperature, or predict how many views a YouTube video will get. Regression helps us make precise, data-driven predictions in a wide range of fields. Clustering is an unsupervised learning task where the goal is to group data points together based on their similarities. Since the data has no labels, the AI finds hidden structures all on its own. For example, document clustering lets an AI read thousands of news articles and automatically group them into topics like sports, politics, and finance. Clustering is powerful for discovering patterns you might not even know exist. Sometimes datasets have way too many features, hundreds of columns, which can overwhelm a computer. Dimensionality reduction is the process of compressing the data, removing redundant or less important features while keeping the core information intact. It's like converting a massive, uncompressed video file into a crisp, lightweight zip file. This makes analysis faster and more efficient without losing valuable insights. Before any model can learn, the data must be prepared. This involves several steps, including cleaning, transforming, and organizing the data. Engineers spend a lot of time making sure the data is in the best possible shape for the algorithm to learn from. Proper data preparation is the foundation for building accurate and reliable machine learning models. Our data is almost always messy and unoptimized. Feature engineering is the creative process of transforming raw data into new features that make it easier for the ML algorithm to understand. For example, instead of giving an AI a raw timestamp like 08:42 a.m., you might create a new feature called is rush hour and mark it as true or false. This gives the AI a shortcut to finding patterns and improves its performance. ORI data isn't always better. Feature selection is the process of picking the most relevant features for your model and discarding the useless ones. For instance, if you're predicting house prices, the color of the front door probably doesn't matter, so you drop that feature. This makes your model faster and more accurate by focusing only on what truly matters. Model training is where the magic happens. This is the phase where you feed your training data into your chosen ML algorithm. The algorithm runs over and over, adjusting its internal mathematical weights until it can successfully look at the features and accurately guess the target variable. Training is the heart of building a smart, capable model. Once a model is fully trained, tested, and ready for the real world, it's time for inference. Inference is when the live model applies its learned knowledge to brand new data and outputs a prediction. For example, when you upload a photo to Instagram and it instantly suggests tags for your friends, that's model inference in action. It's the final step where your model starts making a real impact. Wrap it all up, building a machine learning model follows a clean, logical pipeline. First, you collect a dataset. Next, you perform feature engineering and selection to clean and optimize the data. Then you split the data into training, validation, and testing sets. After that, you run model training using an algorithm like classification or regression. Finally, you deploy the model to handle live inference in the real world. Each step is crucial for building effective ML systems. Let's take a closer look at supervised learning as a concept. In this approach, every example in the dataset has both input features and a known output label. The algorithm's goal is to learn the mapping from inputs to outputs. This is the backbone of tasks like classification and regression, where accuracy and clear answers are essential. Supervised learning is the most widely used form of ML in industry. Supervised learning is all about letting the algorithm find structure in data without any labels. The model explores the dataset, searching for patterns, similarities, or groupings. This is especially useful when you don't know what categories exist in your data. Clustering and dimensionality reduction are classic unsupervised learning tasks, helping reveal insights that aren't immediately obvious. Reinforcement learning stands apart from the other types. Here, the algorithm learns by interacting with its environment, receiving feedback in the form of rewards or penalties. Over time, it figures out which actions lead to the best outcomes. This approach is ideal for tasks where the right answer isn't always clear, but success can be measured by accumulated rewards, like playing games or controlling robots. Dataset is the structured collection of information that powers machine learning. It can include numbers, text, images, or audio, all organized for easy access and analysis. The quality and organization of your dataset directly impact the performance of your model. Think of it as the foundation upon which everything else is built. Training data is the portion of your dataset used to teach the model. It contains both the input features and the correct answers, allowing the algorithm to learn the relationships within the data. The better your training data, the smarter your model will become. It's the main ingredient in the recipe for machine learning success. Testing data is set aside to evaluate the model's performance. It is never shown to the model during training, ensuring an unbiased assessment of how well the model can handle new, unseen data. This is crucial for understanding whether your model will succeed in the real world. Validation data is used during the training process to fine-tune the model. By checking the model's performance on this separate set, engineers can adjust settings and prevent overfitting. Validation data acts as a checkpoint, ensuring the model is learning the right patterns. Features are the individual variables or columns in your dataset that the model uses to make predictions. Each feature provides a piece of information, and together, they help the model understand the data. Choosing the right features is critical for building effective models. The label is the outcome or answer the model is trying to predict. In supervised learning, every example in the training data has a label. This helps the model learn what the correct output should be for each set of features. Target variable is another name for the label. It's the specific value or category the model is designed to predict. In statistics and ML, this term is used to emphasize the focus of the prediction task. Classification is about sorting data into categories. The model learns from labeled examples and predicts which category new data belongs to. This is essential for tasks like spam detection, image recognition, and medical diagnosis. Regression focuses on predicting continuous values. The model learns from examples with numeric outcomes and estimates values for new data. This is key for forecasting prices, temperatures, and other measurable quantities. Clustering groups similar data points together without any labels. The model identifies natural groupings in the data, revealing hidden patterns and relationships. This is especially useful for market segmentation and document organization. Dimensionality reduction simplifies complex datasets by reducing the number of features. It keeps the most important information while removing redundancy. This makes models faster and easier to interpret, especially with large datasets. Feature engineering is the art of creating new features from raw data. By transforming and combining existing data, you can help the model find patterns more easily. This step often leads to significant improvements in model accuracy. Feature selection is about choosing the most relevant features for your model. By focusing on what's important and removing noise, you make your model faster and more accurate. This is a critical step in building efficient ML systems. Model training is the process where the algorithm learns from data. By adjusting its internal parameters, the model improves its ability to make accurate predictions. Training is the core activity that turns raw data into actionable intelligence. Inference is when a trained model is put to work, making predictions on new, unseen data. This is where the value of machine learning is realized, as the model applies its knowledge in real-world scenarios. Machine learning workflow is a structured process. Collect data, engineer and select features, split the data, train the model, and finally deploy it for inference. Each step is essential for building robust and effective ML solutions. See all these concepts in action. Imagine building an email spam filter. You collect a dataset of emails, engineer features like sender address and keywords, select the most relevant ones, and split the data into training, validation, and testing sets. After training the model, you deploy it to automatically filter new emails. This practical workflow is used in countless ML applications. You've covered the three main types of machine learning: the anatomy of data, core ML tasks, and the workflow engineers used to build models. Each concept builds on the last, creating a complete picture of how machine learning works from start to finish. With these basics, you're well on your way to understanding and applying ML in real-world scenarios. That wraps up our journey through the core basics of machine learning. From understanding how data is split to the difference between regression and classification, you've now got a solid foundation. Keep exploring, and you'll discover even more exciting possibilities in the world of ML. See you in the next video.